Okay guys, let's get to the grade 12 geometry revision. I need to say a little bit about what I did in the grade 11 lesson, just so that the grade 12 stuff has a foundation that we're going to build on. But before I get there, let's just quickly go and look at that document. In the course under modules, under announcements, before the previous exam, I sent an announcement with a few exam. Where is it? Tomorrow's exam is this one, yeah. With a few information about that the prelim exams. But together with that, I sent an exam guideline. There's a exam guideline, and in this guideline I give you like a breakdown of the exam. So you'll see there breakdown of the exam. For example, let's see if I can get this a bit bigger. There we go. So for example, you see the content for the final exam, paper 1. This is not exactly perfect because the paper 1 is fine, but paper 2 is not just question 1, 2, 3, and 4. Paper 2 is usually up to question 11. But the first few questions is stats, the next few analytical geometry, then trigonometry. This is just my suggestion for the exam for next year, that they rather just break it down into simple 4 parts since there's 4 topics. So, but what I want to show you here is the geometry. Out of the two papers are added together to give you a mark out of 300. So out of those 300 marks, only 15 marks, that's 5%, is probability. 5% is finance. Okay, what's that? About 12%, maybe 12, a little bit more than 12% is sequences and series. Okay. The biggest marks, the most marks go towards geometry, trig, and analytical geometry. Okay, so it's a very big topic, a very important topic, and yet it's difficult. I must say, Euclidean geometry is not easy. Even I find it difficult and have to think about. Like most of the other work, I can look at it for a few minute or two and I know what to do. But with the geometry problems, the difficult ones, I really have to spend time and try and figure them out. So if you spend a few minutes, well, a minute or so, and you still don't know, just leave it, go on with the rest of the work, leave it for the end. Okay, don't try and waste your time on the geometry problems, but there's some things you have to be able to do in geometry. You have to be able to prove the theorems. And that's what I did in yesterday's lesson. I looked at all the grade 11 theorems which proof we needed to know. Okay, and now we'll go and look at the grade 12 theorems. There's only 2 that's likely to be asked, the grade 12 theorems, and I am fairly sure one of them will be asked. So here's the theorems that you need to know. Okay, a line drawn from the center of perpendicular to the chord bisects the chord. Theorem 1. Angle subtended by an arc at the center is double the size of the angle subtended by the same arc. The opposite angle in a cyclic quadrilateral are supplementary. So these are the grade 11. I'm not going to go through all of them, but here's the 2 grade 12 proofs. There's actually 3 that, according to CAPS, you are supposed to know, but in the exam guidelines they only specify these 2. Okay, so we'll focus on these 2. A line drawn parallel to one side of a triangle divides the other 2 sides proportionally. Okay, so we'll look at that one, and then this one, equiangular triangles are similar. Okay, that look tells me you've never heard that theorem. Okay, so that's fine. Hopefully you get to understand what they are by the end of the lesson. Okay, but please go and look at this document. I really think this is going to be helpful. Fazila, I can even email it to you if you want it. But in it, I just tell you, in paper 1 there's algebra. What should you be able to do in algebra? In paper 1 there's functions and graphs. What are the things that's most common in an exam? So I don't give you examples, I just explain, and you must, next to it, go and tick, I know how to do this, I know how to do this. If you don't, make a note of it and go and study it, or come and ask me, I have no idea what this means, like give me an example of this please, things like that. Okay, so there is both papers explaining what I have found are the most common ways and things that they ask. And so I often use words like it is likely. There will be at least one question relating to circles in the Cartesian plane. At least one question is based on linear regression line. Okay, so yeah, I go and try and show you what is likely or what you can definitely expect. Okay, so let's get to the theorems. In grade 8 or 9, I don't know, I don't teach those grades, but I think it's in one of those 2 grades, you learn what it means for 2 triangles to be congruent. Okay, so let's see if I can. 2 triangles are congruent when, way to manipulate this one. Okay, 2 triangles are congruent when their sides are exactly equal. So for example, if I have triangle here, triangle ABC, and I have triangle DEF, if I know that AB is equal to DE, now the equal sign, and I explained it yesterday as well, equal means they are the same. Now these 2 sides aren't the same, they're not the same side. So the technical word is congruent. Congruent means the same size. Okay, just because you have the same height as another person doesn't mean you are the same person. Okay, so you are in a sense congruent in height. Your height is equal. Okay, so that's the same with distance. But so we should technically use these 3 lines when we say that one side length is congruent to another side length. But we won't. We'll just use the equal sign. Then we know AC is equal to DF or congruent, and then BC is congruent or equal to EF. Now, if these 3 things are true, then we say triangle ABC is congruent to triangle DEF. And you have to keep the order so that if it's AB here, and AB is the first 2 letters, then the first 2 letters must be DE. If I have BC and EF, BC is the last 2 letters, so the last 2 letters here must be equal. Do you understand? So that is important when you write that down. So what this means is that their sides are equal. Now, if I knew that instead of the side, I know that the side and 2 sides are equal. So for example, this side is equal to that side, and this side is equal to that side. And I know that this angle that the 2 sides make, in other words, the inclusive angle, if we know that the inclusive angle is also equal, then it also means that they are congruent. Because if these 2 angles are equal and these 2 sides are equal, then this 3rd side doesn't have a choice. These 2 sides have to be the same. Okay, so it's what we call a corollary. It is, if this is true, then this will also be true. Also, if I have instead of this, I have that 2 angles are equal. This angle is equal to that angle, and this angle is equal to that angle. So in other words, I've got 2 angles are equal. Then if I can just get one more side to be equal, any side, doesn't matter which side, doesn't matter if it's these 2 sides, then so any 2 angles and any one side, then it's also congruent. Okay, so these are important, and the reason why I say this is because we're going to do this in one of the proofs. We're going to have to show congruency, so that's why it is an important introduction. Then finally, what if I had, because I had 3 sides, 2 sides, 1 side, what if I had no sides? Would a triangle with 3 angles be congruent to another triangle that has the same 3 angles? And the answer is no. Let me give you an example. Here's a triangle, and here's another triangle. Now in this triangle, these 2 sides are parallel. which means that this angle is equal to that angle. You guys know your parallel theorems. So this is the F in fun, and then this angle is equal to that angle. And then this angle, they also have in common. You see, both of these triangles have this angle in common. So here we have two triangles, and in the two triangles, the bigger one and the smaller one, they've got three angles that are equal to each other. And yet, we can see that the one's sides are all smaller than the other one's sides. You see that? So these two are not congruent. Congruent means all of their sides are equal. So so angle is not congruent. That is what we call similar. And all the grade 12 theorems is about similar triangles. It's about the relationship when we have two triangles that are similar, and how their sides are then proportionate. Okay, so we'll look at that in just a minute. The last one for congruency is not going to be applied really, but that is if I have a 90-degree angle. Remember, if they give me a 90-degree triangle, they already gave me one of these two. So either I then have these two sides, so I've got two triangles, and in the two triangles I know that these two sides corresponds and those two sides corresponds. Then I have two angles and an inclusive, two sides and an inclusive angle. So then they're congruent because of that law. But let's say they didn't give me one of these two sides. They gave me two sides, but not one of these two. So let's say they told me that those two are equal. Now, in a 90-degree triangle, that will also mean that this third one must also be equal, because if two of them are equal, then I can use Pythagoras to get the third one. And Pythagoras will give for both of them the same answer because the other two sides are the same. So in a 90-degree triangle, there is a special one where if I have the 90 degrees, the hypotenuse, which is now that one, the one opposite the 90 degrees, and any other side, then I also know that these two triangles would be congruent. Okay, so let's go and look at some of the grade 12 theorems. Okay, now when it comes to knowing your proofs, the proofs can be complicated, but usually it just depends on knowing the construction. Once you know the construction, you know the trick to the proof. Now, in doing the grade 11, I would really encourage you to go and watch that if you didn't, because the grade 11 proofs, there's, I think, how many would you say there was that was a little bit complicated? Two, maybe three is slightly complicated. Not really, but slightly. And the rest are also simple. If you just get the one, you get them all. Now the grade 12 ones, those two are both fairly complicated. Okay, not difficult. Just you have to just remember a few things. But once you get that, it's not that bad. Now I don't know the proofs off by heart, but I figure them out as I go around. I just remember the important construction, and then I remember the idea of the proof, and the rest I just do my calculations correct, and then I remember it. Okay, so before I get to the proofs that we actually need to know, I need to tell you a theorem that is going to be needed. Okay. First of all, the area of a triangle. I'm not going to give you the proof for the area of a triangle. You guys know this very well. What's the area of a triangle? Thank you. Half base times perpendicular height. Okay, that means it doesn't matter what your triangle looks like. I'll draw a normal one first. What we mean by half base times perpendicular height is from the apex. So we put one of the sides as our base. Then the apex is the side that's opposite this side. And from there we just drop a perpendicular line down until it reaches the same level as the the base. Once we have that, then our area is this is the length of the base. We take half that length and then we multiply it by height. Now, it might just be interesting for you to know, but what the proof relies on is, what is the area of a rectangle? Length times breadth, isn't it? So here's the breadth, which in this case would be the base, and the height would be the width. So a triangle covers exactly half the space. In other words, when we take half of it, we're also taking half of it away. So in other words, if we were to take these two shapes, you'll see if I just flip these two around, I'll make another one of this shape. Understand? So in other words, this shape here is congruent to that one. So I actually never realized it. That's how you prove it. You show that these two are congruent. These two triangles are congruent because there's a 90 degree and a 90 degree. Okay? We know that this length is equal to that length. This length is equal to that length. So all three sides are equal. Same with this one. So these two are congruent, which means they're exactly the same. So the area must be the same. And these two's area must be the same. So if all in all the area is length times breadth, then if I just take half of the triangles, then the area is just half of that. Okay? So the area of a triangle is then this half base times that perpendicular height. Okay, now another type of triangle looks like this. Okay? Here's my base. Now look at my apex. My apex, if I drop a perpendicular, it doesn't fall on top of my base, do you see? Okay? But it doesn't mean it's not still the height. It still applies exactly the same. Okay? This is still my height and that is still my base. It's just my height is just not over it's like a crane. Okay? Instead of a thing hanging from a roof, it's like a crane hanging off. The height from the floor is still the same. Does that make sense? Okay? Same thing. This one's area would be half the base times perpendicular height. Okay. Now, if that is true, all I need to know is not necessarily how high the apex is. All I need to do is, if I can draw a perpendicular line, a line through the apex that is parallel to my base, okay, then all I need is the distance between these two parallel lines. Does it make sense? So to find out the area of this triangle, all I need is to find the distance between the base and a parallel line that the apex goes through. Is everyone okay with that? Now, does it then make sense to you that if that is true, and I take another triangle, any other triangle, and I start between the same 2 points, in other words, they've got the same base, and they go and both of them have the same height. In other words, if I connect their vertices, not their vertices, their apexes. What is the plural of apex? Apices, I don't know. But anyway, if I do connect them, then there's a parallel line between these two, which means that they have the same vertical height or perpendicular height above the base. Does it make sense to you that these two triangles have exactly the same area? Why do they have the same area? Same base and same height. Okay, so this is one of the theorems that triangles that have the same base and their apexes connect to can be connected to make a parallel line with the base. Means they are two triangles between parallel lines with the same base. Okay, then they will have the same area, and I mean it's very simple to see why. Is that okay? Okay, so if you're okay with that, we can go on to the first theorem. Okay, the first theorem says that if I have a triangle, you guys can see that, don't you? If I have a triangle and I draw a line parallel to one of the sides, so I'm just going to choose this bottom side because it makes the picture look easy, but I draw a line parallel to that side that cuts the other two sides somewhere. So now I've got triangle A, B, C, D, E, and then BC is parallel to DE. Then the theorem says is that then the sides are proportionate. So in other words, AB, the line cuts the sides into two proportional parts. In other words, AB divided by BD is equal to AC divided by CE. Now, I think you guys don't really understand what that means. Do you know what I mean by this? That there's a proportion now in the sides. You feel you know what that means? Okay, let me explain it like this. Let's say this side length here is 4, and then this side length here is 6 units. Then if I take 6 divided by 4, I get 1.5. So 3/2. That means that AC over CE must be some relationship that's also 3:2. It doesn't mean this one is 3 units long and that one is 2 units long, but if I divide the 2, I must get 3/2. So instead of saying 3/2, I'm going to say this one is 3 times x and that one is 2 times x. So when I divide it, so I don't know what x is, some factor, but whatever x is, I must multiply both those sides. Okay, so that if I divide these two sides and those two sides, I must get the same ratio or fraction. Does that make sense? What that means? Now that is what this theorem says, is that's what this parallel line does. So for example, you get the midpoint theorem. The midpoint theorem says that if I connect if I draw a parallel line from the middle of this one parallel to, so this one is now 10 units, so let's say I divide it into 5, and it's parallel to this line, then it will also halve this side. Okay, so it's actually a very useful application, because let's say I wanted to find the middle of this line, exactly the middle of that line, but I can't get to it. But what I could do is I can find, like let's say here's a big gap over here and I can't get to the middle there, but I want to make a middle mark here. Then I could take a laser, okay, and point the laser parallel. I can find the middle of this one because maybe I have access to that one, and I can then point a laser parallel to this side towards that wall, and it will be exactly in the middle if I started at the middle parallel to that side. Okay, so it is quite useful. Now, to prove this theorem is going to take is quite a complicated proof. Okay, I think there's a simpler proof, but I'm not allowed. I don't know if it's allowed using using the sine rule, but we'll stick to the proof that they want us to use, and that would be fine. Okay. First of all, what we'll do is we'll need to draw our two constructions. Now I'll draw the one construction and do a proof, and then I'll draw another construction and I'll do the proof there. Okay? What I'm going to do is I'm going to start with drawing a perpendicular line from, so imagine this is the base. Okay, this is going to be my base. So if AB is my base, where's my apex? C. So from C, I'm going to drop a perpendicular line on the base. Okay, now since it's a construction, and I'm going to call it H. I'm going to call this line H. Now I want to do the same thing, but I'm going to do it with AC. So on AC, I'm going to draw a perpendicular. There's AC's base as my base. Then from B, which is now my apex, I'm also going to draw a perpendicular line on AC. And I'm going to call that one K. Okay, so my construction is, if I write it, the construction is, before I write out my construction, I think it might be helpful if you know where I'm going. Then you might understand, why am I making this construction? What I want to do is I'm going to take the area of triangle ABC. Area of triangle ABC. Then I'm going to divide that area of triangle ABC with the area of triangle DBC. So in other words, later on I'm going to make another construction. I'm going to create this triangle here. You see triangle DBC? Okay? Now, so then I'm going to have area of triangle DBC. I'm going to divide it with each other. Now notice why. Because if I do, I'm going to have, for these two, we'll have, now in triangle DBC, which one is my base? No, sorry, not which one. I'm going to make DB my base. So notice what I'm making my base. I'm making the base AB for the top, and I'm making my base DB for the bottom. Okay? Now, if DB is my base, which is my apex? C. If C is my apex, what is my height above DB? I wish I could turn this page to show you. Maybe try and turn your head. Wait a minute, let's do this. There we go. If DB is my base, what is my perpendicular height? I already drew it. What do? I go to my apex and I drop a perpendicular height from there. And I've already done that. The green. Do you see? The perpendicular height for triangle ABC is the same as the perpendicular height for triangle DBC. Now they don't have the same base, but they do have the same apex. Both of them have C as the apex, and both of them's base are on the same line. You see, their bases make together one line. So they have the same height. Now, so can you see now where this is going? So, for example, this triangle ABC is going to be half the base, which is AB, times the perpendicular height, H. and then I'm going to divide the area of DBC with a half AB, sorry, not AB, DBC, the base is DB, but it has the same perpendicular height. Now notice, now these will be able to cancel, and then I'll be left with AB over DB or BD. You see that? Now on this side, that is the one fraction I'm going to look at. Then on the other fraction I'm going to look at is now the exact same thing but with this side. So on this side I'm also going to have triangle ABC, but for this one I'm going to draw another, I should have done this one in a different color. So there was my one construction. Then I'm going to do another construction from here so that I exactly the same thing. I've got the apex B, and it's the apex for ABC with perpendicular height K if AC is my base, and then I've got that B is also the apex for CBE, and K is also the perpendicular base. Okay, so in other words, I'm going to have I'm going to have that the area of triangle ABC divided by the area of triangle BEC, CEB is going to be given by a half AC times my perpendicular K, because this one I call K, divided by a half CE times perpendicular K. And the same thing, these cancel. Okay? But now I've just shown that this thing simplifies to this and this thing simplifies to that. Now I need to show that these two areas, these two fractions are equal. Because if both of them simplify to this, but the original fractions is equal, they must be equal. So for example, look at the top. They both have the same numerator, the area of triangle ABC. Both of them are working out the area of this triangle, but each one just uses a different base. But it's the same triangle, so it must have the same area. So it's easy to show that the numerators are equal. To show that the denominators are equal, notice that I've got, here's my one triangle, the one that I made with the pink. No, I lie. I made it with orange, and here's the one triangle, okay, that had apex C, and here was my other triangle that I made with pink. Okay, that's CEB. Now, why, can you maybe tell me why would these two triangles have the same area? I know these two triangles have the same area because they're the same triangle, but why would these two have the same area? Can you see? Opposite vertical angles? No. Maybe I don't understand what you're saying. These? No, that doesn't necessarily make, because this one, I can extend this one just longer and that one longer, and it wouldn't change these angles. It's just upside down. They have, if I make BC the base, then D and E is the apex, and the line between D and E would be parallel to the base. That's exactly this theorem. What was it called? Let me just quickly see. It's not this one. Just want to see the shorthand for that one. It's called the no, I don't know. I didn't put a shorthand. If two triangles share a base and their apex line, and their apexes line on a line parallel to the base, then the area of the triangles are equal. So you can maybe just say shorthand, same base, apex equal distance. Does that make sense? Just a short way to say that's why you say. So in other words, if they have the same base and the apexes have the same distance from the base, then they must have the same area. And that's exactly. And since we then have that to be true, that the denominators are now also equal, it can only follow that these two fractions have to be equal. And if these two fractions are equal, then, and both of these two fractions simplify, the one to AB over DB, the other one to AC over CE, it means that AB divided by DB is equal to AC divided by CE. Does that make sense? Okay, so let me just quickly write out the whole proof for you so that you can see how we'll do it. Okay, so it feels like I'm going to just repeat everything now, but now you understand what my aim is, why I'm going to write my construction. Construct perpendicular H from C onto AB. Now, how you write your construction, as long as it makes sense. Okay, if you wanted to, instead of calling it perpendicular, you wanted to call it that, you wanted to say that one is M, then you could have said construct CM perpendicular to AB. That's also, so it doesn't matter how you phrase it, as long as the person can read it and look in your sketch, okay, makes sense. Okay, so don't worry about being technically correct, just be clear. Okay, and so that we can understand what you do. And so, how am I going to do it? Am I first going to, okay, let me say this. I'm first going to prove that the numerators are equal. So I'm going to say construct that one and construct, so let me do it in a different way so that at least I'm not repeating myself. Construct Bn, so I want to do Bn perpendicular to AC. You guys understand what I meant when I wrote it like this? Is that okay? And so now I'll say in triangle ABC, the area of triangle ABC is equal to a half AB, which is now my base, times my perpendicular height. I've now called it CN. Okay, or area of triangle ABC is equal to a half AC divided by, that's now my base, and now BN is my perpendicular height. Now again, you could have called them H and K, and you would have just had an H and K there, doesn't matter, as long as you keep the CM and BN later on when you use that height again. Okay, and so therefore, because these two are equal, those two must be equal. So in other words, a half AB CM must equal a half AC times BN. So far, I've proven now my numerators. Remember, I've got now those two. Eventually, I'm going to take the area of this triangle divided by the area of that triangle, and the area of this triangle divided by the area of that triangle. And then I wanted to show that those two fractions are equal. So far I've shown that the numerator of those two fractions are going to be equal. So I'm just going to put this on this shelf and I'm coming back to use it later. Okay, now I'm going to look at my denominator. So now I need a new construction. I haven't done that yet. Construct line DC. Now I have a new triangle, and in triangle, and that's now called triangle BCD, we now have that the area of triangle BCD, is now equal to a half. And now just remember what you want to use your base for. So what I'm trying to say is just remember what you want to make the base. The two sides that you want, or the two portions of that side that you want to make use as the fraction. In the fraction is what you want to make the bases. So in this one, that's going to be my one base. So even though later on I'm going to show that these two triangles are equal because they have the same base, that's not the base that I use in this case. I want to use that base so that I can use that height. So in triangle, it is a half, what was that? B, D. I think it was BD, eh? Yeah, half BD times the perpendicular height. I've now called this perpendicular height CM. So times CM. Okay? And also construct line CD and line, now I'm going to draw this triangle, BE. So I've now shown that in the one triangle I've got that, and in triangle BC, is it? Yeah, BCE now. In triangle BCE, the area of triangle BCE is equal to a half, and now my base is the CE. Half, I should try and make it a bit smaller, is a half CE times, now my perpendicular height is BN. Okay, and just like in this one, the two areas are the same. This case it was easy because it was the same triangle. This case I have to actually use a theorem to show, but the area of triangle BCE is equal to the area of triangle BCD, and then the reason I give is same base, and then just so that the person that's reading actually knows know what you're talking about, just name the base. Same base BC between or let's say triangles with same base BC between parallel lines. And then just name the parallel lines. BC, DE. BC parallel to DE. Okay, and therefore I know the areas are the same, and then I can use the two expressions that I got. That expression and that expression must therefore be equal. In other words, a half BD CM must now be equal to a half CE B times BN. Is that okay so far? It's not difficult. You can see it's a intense proof. It's a long proof. Now I'm just going to name this one equation 1 because it's still just an equation. It's not simplified yet. If you want to, you could simplify it by cancelling the half on both sides. because you just multiply both sides with 2 and then the half is gone, and the same here. So you can do that, and then we call this one 2, and now I'm just going to say take equation 1 and divide it with equation 2. In other words, take this side, divide it by that side, and what do I get? AB times CM divided by BD times CM is equal to AC times BN, I'm taking the right hand side now, divided by CE times BN, and now you simply cancel. And there you've proved that AB divided by BD is equal to AC divided by CE, which is what we wanted to prove. Okay. Okay, prove that. In other words, they give you that these sides are proportionate. Okay, if what you're asking is the converse of this theorem. So converse is when we take it from the opposite way around. So in other words, they now give you what this one would ask you to prove. The converse theorems aren't examinable, so they can't ask you that, but I like that you ask it. It's still good to know how to prove the opposite way around, because it gives you understanding into the geometry. It not just gives you understanding of the proof, but into the actual geometry and how it's applied. So let me just quickly think how it works. If you want to prove that lines are parallel, you obviously want to use the opposite, the converse of your alternate angles and things like that. So for example, if you can prove that this angle is equal to that angle, if you can prove that, then you've proven that these two are parallel. No, so if these are equal, then the lines have to be parallel. But she's asking that we have to prove that they are parallel. We don't know they're parallel.
So saying those two angles are whatever.
That's what I'm trying to figure out now. So if I can show that those two angles are equal, then I know, and I have to use this to show it, that those two angles are equal. And if I can use that to show it, then I've done. I want to end up taking the shortcut here, and then showing you how to do it using trig. Okay, because I'm trying to show two angles are equal. I think it's fine. Let me just try it. I don't know if I'm going to get it right. I don't mind getting it wrong, but let's try it. Let's say this is what we knew. We know that AB divided by BC is equal to AD divided by CE. AD divided by DE, yeah. Sorry, I'm already trying to think. Okay, if D, DE. Kind of what I think you're going to have to do is drop a perpendicular here, okay? A line that is perpendicular to there, and another line that's perpendicular to here. Now it is going to be it is going to be the same line if I draw it perpendicular, but because I can't assume it's parallel, I can't assume that line will go through both. Okay, the reason why I'm doing that is because I want to get this height. Now, how we get height of something is always using sine, because sine. So I want to show that B. I want to show that B's height and D's height is equal. Okay, they're opposite, equal, and the reason why I use that is because look what's going to happen if I take sine. Sine of B is going to be opposite, which is, let's call this height, opposite, which is the height, divided by the hypotenuse, which is AB. Okay, and so I get that my height is equal to sine B times AB. And then for sine D, I get that sine of D is equal to same thing, the height, that H, divided by AD. So notice there I've got my AB and my AD, and I know that these two, so if I solve the height of these two are equal. So in other words, AD sine D. Now, since they have the same height, I know that AB sine B is equal to AD sine D. So now I know if I divide both sides with AD, on this side it cancels, and I divide both sides with sine B, I see that AB divided by AD is equal to sine of angle D divided by sine of angle B. But AB divided by AD, so in other words, if I take this one and I divide it there, and I take this one and I multiply it there, then I get BC over DE is equal to AB over AD. Do you see what I do there? I'm just mixing this up a little bit. So this is also equal to BC over DE. Okay, don't know if it's going to be helpful, but let's now look at, yeah. It is, because look, the height for both of these triangles, the height is given by the same height. So in other words, the way I get something's height is I take the angle, sine of the angle B, times the hypotenuse. AB. I'm not saying that AB sine B is equal to AD sine D. I'm saying that AB sine B is equal to the height. AD sine D is equal to height. but the two heights are the same. That's why the two expressions are equal. You understand? Okay. Now, I really want to do it, but it feels like I'm going to waste a bit of time trying to figure it out. So, let me just hang it here. Okay, let me just go on to the next proof that we have to know, because my time is a bit limited today to go and collect the exams. But yeah, maybe if I finish early, then I can finish this off. But that would be the idea, is you're kind of using the sine rule, and I didn't even have to use h. I could have just used the sine rule on this one and the sine rule on the top one. The only problem is, why I just don't want to go on immediately, is the next triangle I'm going to work on is this big triangle. And now I first will have to show you, I'll have to convince you, you won't have to convince your marker, but if I'll have to convince you that if this one divided by this one is equal to that one divided by that one, then it is also true that this one, the small one, divided by the whole size, the sum of the two, is equal to this one divided by the sum of the two. Not a difficult proof, but it's going to take some time just to show you that. And I can just tell you, and then it's easy to go on, because then I can show you that that AC divided by AE is equal to sine C divided by sine E, and now I've shown that this would be equal to that. So in the end we will have that sine D divided by sine E is equal to sine C divided by sine D divided by sine B, sine C divided by sine E. So you is that true? Sine dB. So in other words, sine D no, I did it the wrong way around. Sine AC sorry, it's this way around. Okay, that way around. So this one is E and C. Sorry, I've now skipped a few lines. That's why because we would multiply this one there. So this one would have been AC sine divided by sine E, and when I multiplied that side. Okay, so anyway, or AC times sine C, and then the sine C is divided on the other side. That's why he's at the bottom. But then in the end, now you've got AC over B. So now, and it doesn't immediately follow, but that was the direction I was heading in. That means if these two fractions are equal, then D must equal E, and B must equal C. You see that? It's not 100%. I'm not happy with that because it's a fraction. So it doesn't necessarily mean that if one fraction is equal to another fraction, that the numerator is equal to the numerator, because 2 over 4 is equal to 1 over 2. Doesn't just mean that these two are equal. So something wrong in my proof, and I'll have to go and figure out. It's going to take a bit of time. Okay, but thank you for asking it. It's a good question.
So we don't need to learn the Equiangular Converse theorems?
No, all the grade 12 Converse theorems. No Converse theorems are examinable. Okay. The next theorem that we need to know, let me just see if it's here. There's a midpoint theorem. I'll just quickly go through the proof. The midpoint, we've already looked at it. No, I'm not even going to look at it. It's too trivial, okay, for time's sake. The next one that is quite important is that if, where is it? Equiangular triangles are similar. Okay. Now, what we mean by similar is that their sides are. Yeah, I define similar triangles a bit abruptly when I said when the angles are equal, they're similar. Okay. This is the proof that when the angles are similar. When the angles are equal, they're similar. Equiangular, equ means equal, angular means angles, so equal angle. Equiangular triangles are triangles that have all of their corresponding angles are equal. Okay, now they are similar. Now what it means for triangles to be similar is that they're similar if their sides are in proportion. In other words, if I take the one side divided by the other side, I can take another side and get the same answer by dividing by the corresponding side. That's what similar technically means. Now, in this proof, we want to show that equiangular, if the angles are equal, that they are similar, so that you can use it as a definition, almost. That to have angle, 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 you actually have a similar triangle. Okay. So this one is really not difficult to prove. It's actually a very easy proof, but it's also a long proof. Okay. So and the point is they don't have to give you a sketch. Usually they give you a sketch and you must use their sketch. But if we say equiangular, you must immediately know I'm using two triangles that have the same angles, equal angles. So let's do that. So if they're not the same size. So let's draw one, okay, triangle, and that one looks way too neat. Okay, so there's my one. Now I'm going to draw another one that I'm going to try and draw it so that this one just looks like a smaller one of that. And that's basically what similar means. Similar means it's the same shape but different size. Basically, that's what it means. It's in proportion. So you are going to be given triangle. So you probably they will tell you given triangle ABC and triangle DEF. Okay, where angle A is equal to angle D, angle B is equal to angle E, and angle C is equal to angle F. So this is what they give you, two triangles with equal angles. Okay, and here's going to be the proof. In this proof, the aim of the proof is to reconstruct our previous theorem. In other words, I want to show that that I'm going to copy this triangle into this triangle, and if I do that, then I'm going to create a side length, and if I can prove that this side length is parallel to that side length, then I know that this side divided by that side is equal to this side divided by that side, and then I have the similarity that I'm looking for. Okay, so let me show you the construction. The construction is very simple this time. Construct. I usually construct an M and M. Construct N on AB so that AM is equal to DE. In other words, I'm going to construct a point here so that I know that this length, that's my point M, is equal to that length. And then I'm going to construct n on a C so that an is equal to df. So now n is somewhere here, and I want n so that these two side lengths are equal. That makes sense? And then you're just going to construct n. In other words, you're just going to connect them. Okay. So basically, you copied this triangle here, but you don't know yet if these two are congruent, if they're exactly the same size. Because all you did was to show that two of these sides are equal. And for congruency, we need to know three sides are equal. And you don't know that mn is equal to ef. Okay, you can't just assume that they're equal. But what do we know about our triangles? We do know that in triangle AMN and triangle DEF, in those two triangles, I do know that AM is equal to DE. AN is equal to DE. Why is it equal? So now we need to give a reason. Why is AM equal to DE? They're not the same side. Same side means it's the same side. Like it's this. MN is equal to MN itself because it's the same side. Yeah, construction. We constructed it like that. Does that make sense? I drew it like that. Okay? Then also AN is equal to DF. Why is AN equal to DF? Same reason, construction. I constructed it like that. AN equal to DF. We constructed it. So we chose M to be so big. So we're not trying to do it on our sketch perfect, but we're assuming we did. So it's not about it. We are saying let's find that point M so that it's true, and we are allowed to do that. You can construct anything with your hypothetical. But you can't, after you've made these two constructions, now say, well, MN is equal to EF. You now have to prove that your 2 points that you constructed are equal to EF. And I'll show you, this is what I'm trying to show you, that we have indeed, that these two triangles are congruent. Okay? Now, the other thing we know is that angle A is equal to angle D. Why is angle A equal to angle D? Now, for example, here's my phone and my pen. They're equal. But just because I've got two equal sides, I can make any angle in between. My question is, why do we know that angle A is equal to angle D? Remember, these two triangles were given to us in the beginning. And in the beginning, they told us they are equiangular. They told us A is equal to D. So it was given. So it is given. So now look what we've shown in these two triangles. We've shown that two sides are equal. In these two triangles, we've got two sides that's equal, and the inclusive angle between them is also equal. So we have shown that triangle AMN is congruent to triangle DEF. That means they are exactly the same in shape and size. And the way we've done it is by showing that there's a side, an inclusive angle, and another side that's equal. I didn't have to prove it in that order, side, angle, side. You could have, that would have been neater and maybe made more sense to you, but as long as the angle is between the two sides, it doesn't matter where you've proven that. Okay, does that make sense? So now that we've shown that these two triangles are equal to each other, what we could do is use this one as a replacement for that one. Okay, now if these two angles are equal, if these two triangles are completely equal, it does mean that angle, and now we can number them if I want to, angle M1 is equal to angle E. Does it make sense? Because those two triangles are equal. So, but what reason do I give? From congruence. So because I've proven that they are congruent, now, but I also know that angle E is equal to angle B. But angle E is equal to angle B. Sorry, I'm now I've run out of space here at the bottom. Angle E is equal to angle B. Why is angle E equal to angle B? It was given. Okay. That means if this angle is equal to that angle and that angle is equal to this angle, can you see why it follows that M1 is equal to B? M1, so M1 is equal to B. Now if angle M1 is equal to angle B, what does that tell me? What can I now conclude? The lines are parallel. Therefore, MN is parallel to BC. And the reason that I give is because this is called corresponding angles. They correspond with one another. If I move this angle down, you'll see it fits, it corresponds to that angle. So corresponding angles are equal. Okay. And now, since I know that they are parallel, I therefore know, therefore, my previous theorem that I just proved showed that then the sides are proportional. In other words, AM divided, so this side divided by that long side, AM divided by AB is equal to AN divided by AC. Okay, so that's also what I tried to show in the previous one. If this side divided by that side is equal to this short side divided by that short side, then this short side divided by the long side is equal to that short side divided by the long side. I still do want to prove that to you. Okay? If this is true, that's not what I wanted to show. Remember, I want to show that these two triangles are similar. I've just shown that these two triangles, the big one and the one that's smaller, I've shown they are similar. So to continue further to show that they are similar, I'll have to go and just remind my reader that AN is equal to DE construction and AN is equal to DF. Sorry. construction. So I can just replace these two values now with dE over AB is equal to dF over AC. And so I've shown that this divided by that is equal to, and you actually need to just change the order a little bit. So again, cross multiply and simplify so that you have one triangle in the one and one triangle in the other one. Here we have the two combined. So in other words, if I have AC divided by AB, so I multiply this to the top and I multiply this to the bottom. Or actually, this to the top and this to the bottom. So I've got AC over AB is equal to DF divided by DE. So AC divided by AB is equal to DF. You see corresponding sides are divided by DE. Okay, and that's that proof.
If we ask you to determine if two triangles are congruent and you find them to be similar, what do you do? In other words, you get angle instead of angle.
Okay, so angle means that they are from this theorem now. This theorem now tells us if we have three angles that's equal, they are similar. Okay? Similar is not the same as congruent, because here we see a very good example of two triangles that's similar, but they're not congruent. However, notice now that I duplicated this triangle kind of here. So imagine I now just moved this triangle to be here so that this is now DEF. Okay? Now, if I can just get one of the sides, so I've shown that two triangles have the same angles. If I can just show one side length to be equal, then I know that they are congruent as well. So in other words, if you can show two angles are equal, if you know two angles are equal, you know the third angle is equal, because 180 minus the other two. So if two angles are equal, the third angle has to be equal. So if I get two angles equal, I know already it's similar. Now I just need to show that one side length in the two triangles are equal to another side length in the other triangle. If that's the case, like in this case, you can see it's not true. This side is much smaller than that side. But if I were to be able to make this one bigger until this side is equal to that side, what's going to happen? This side will be equal to that side, and this side will be equal to that side. You see, so if I can just find, if it's what you say, we've shown two angles equal, or three angles equal, I still need to find at least one side on the two that's equal.
So you cannot conclude that they're congruent if you found only the present.
No. Three angles. Yeah.
Because we were doing something like that between the and we only found three angles.
I'll do some examples, maybe we come across one.
Okay.